December 20th, 2025. Shougang Shuicheng Steel Mill, Liupanshui, Guizhou. A turbine starts spinning that fits in a single room, compact enough to fit through a standard doorway, roughly the size of an industrial refrigerator. It generates 15 megawatts of electricity, and it doesn't carry a single drop of water inside. This is Chaotan One, the world's first commercial supercritical CO2 power plant. It just went live, and it runs on waste heat from the steel furnaces around it, the shimmering air rising from casting operations and rolling mills, heat that had always escaped unused into the sky. No fuel burned, no combustion. Just heat that was escaping into the sky, now turning a turbine a tenth the size of the steam turbine next door. By May 30th, 2026, the second 15-megawatt unit connected to the grid, 30 megawatts total, built by the Nuclear Power Institute of China under state giant CNNC. That's not a prototype, that's a commercial plant feeding the grid right now. Steam turbines have run the world since Charles Parsons invented the first one in 1884. Every coal plant, every nuclear reactor, every geothermal station turns water into steam, spins a turbine, and makes electricity. But water has a hard physical limit. Water boils at 100 degrees Celsius at sea level. Modern plants push superheated steam to 600 degrees or more, but water is light. Its molecules are small and far apart even when pressurized. You need massive turbines with enormous blades to capture the energy from all that steam rushing through. A 500-megawatt steam turbine can weigh 500 tons and fill a building the size of an aircraft hangar. Even then, efficiency tops out around 40 to 45%. The rest escapes as waste heat through cooling towers, that shimmering haze you see rising from power plants on the horizon. That's just thermodynamics. No one's beaten it in 140 years. China just beat it, not with water, with carbon dioxide. Every substance has a critical point, a specific temperature and pressure, where it becomes a supercritical fluid, transforming into something that behaves like neither a liquid nor a gas, but something denser and more energetic than either. For water, that's 374 degrees Celsius and 221 bar of pressure. For CO2, it's 31 degrees Celsius and hot coffee and a scuba tank. Temperatures and pressures you encounter in everyday industrial equipment. You can hit supercritical CO2 with industrial waste heat. When you do, the fluid becomes incredibly dense, heavier than steam but flowing like a gas, meaning it moves through turbine blades with far more molecular mass pushing them. That density means you extract far more energy per unit of volume. The turbine shrinks. A supercritical CO2 turbine, generating the same power as a steam turbine, can be 1/10 the size. And because CO2 stays supercritical at higher temperatures than water can tolerate, it doesn't boil back into vapor at those heat levels. Thermal efficiency jumps, meaning more of the input heat becomes usable electricity instead of wasted warmth. Chaotan One is the proof it works in the real world. The plant sits inside the Shougang Shuicheng steel mill because steel making generates enormous amounts of waste heat from furnaces reaching 1,500 degrees Celsius, from casting operations, and from rolling mills. Chaotan One captures that heat, runs it through a heat exchanger, essentially a metal wall, where hot industrial air on one side brings CO2 on the other side above its critical point, transforming it from ordinary gas into supercritical fluid, and spins the turbine. The engineers watched the first readings come through as 15 megawatts flowed into the grid. 15 megawatts from the first unit, another 15 from the second, which came online 5 months later. 30 megawatts total, feeding directly into Guizhou's grid. No combustion, no emissions from power generation. Just recovered energy thrown away for over a century. The turbine hall is a fraction of the size needed for an equivalent steam plant. It's already scaling up. China Energy Investment Corporation has successfully tested a 169-megawatt supercritical CO2 generator. That's the first unit of that scale anywhere in the world. 169 megawatts from waste heat. That's enough to power roughly 135,000 homes. The turbine is still vastly smaller than a steam equivalent would be, still small enough to fit in a large warehouse instead of filling a building. The jump from 30 megawatts to 169 megawatts shows this isn't niche, it scales. Industrial processes operate at 400, 500, 600 degrees Celsius or higher, far above what's needed for supercritical CO2. That heat has been venting into the atmosphere since the Industrial Revolution because there was no efficient way to capture it at scale. Now there is. The Rankine cycle, steam-based power, has been the backbone of electricity for over a century. Every thermal power plant in the world uses it. You heat water, make steam, spin a turbine, condense it back, and repeat. But the equipment is massive, efficiency is locked by water's properties, and waste heat is unsolvable. Cooling towers dump 50 to 60% of fuel energy into the sky or rivers, energy that could do useful work but instead rises as waste. Supercritical CO2 operates at higher temperatures, so you extract more useful work per unit of heat. The turbine is smaller, meaning lower construction costs, smaller footprint, faster installation. Because CO2 stays in a closed loop and doesn't corrode like steam and the water vapor it produces, maintenance is cheaper. And tell me something, where in the world are you watching this from, and what time is it there right now? Drop it in the comments. And subscribe if you're new. This is where the most extraordinary stories come alive. China didn't invent supercritical CO2 power cycles. American and European researchers studied this for decades. The US Department of Energy funded research. Sandia National Laboratories ran test loops in laboratories, carefully documenting findings. But no one in the West built a commercial plant. No one took the leap from lab to grid. China did. Chaotan One crossed that line. It generates power people use. The 169 megawatt unit shows they're not stopping. The West invents technology, publishes research, debates economics, waits for private sector movement. China reads the research, builds the prototype, scales it, and ships it. That's the pattern with high-speed rail, EVs, and solar panels. This is about what happens when a country treats industrial efficiency as strategic priority. China built the most energy-hungry industrial base in human history. Steel, cement, chemicals, aluminum, glass. All run hot. All generate waste heat. Now they've built technology to turn that waste into electricity at commercial scale. Every steel mill is a potential power plant. Every cement kiln, every refinery. That's thousands of sites adding megawatts without burning fuel. In the West, waste heat recovery is niche. In China, it's infrastructure. And that changes heavy industry economics. If your competitor generates power from heat you vent, they undercut your production costs permanently. Supercritical CO2 turbines are more compact and efficient than steam, but research continues into higher temperature operation, pushing efficiency further toward theoretical limits. There are studies on using supercritical CO2 in next-generation nuclear reactors, replacing the massive steam systems that take up acres of space. There are proposals for concentrated solar thermal plants using it instead of molten salt. Every application where high temperatures and compact equipment matter is potential. China is leading commercialization. The 169 megawatt test isn't the ceiling. It's proof the technology scales past demonstration. The next step is likely 300 megawatts, then 500. At that point, utility-scale power generation from waste heat flips the economics of energy-intensive manufacturing and shifts geopolitical balance. Building supercritical CO2 systems isn't trivial. Pressures are extreme, 74 bar minimum, and real systems run higher. The turbomachinery handles a fluid unlike anything most engineers trained on. Seals, bearings, materials, all designed for conditions that don't exist in steam plants. The cycle must stay in a narrow temperature and pressure band. Drop below critical point and efficiency collapses. Exceed material limits and components fail. But China built the expertise. They didn't wait. They ran pilots, learned from failures, refined designs, and scaled. That's the lesson. The technology was available to everyone. The difference is who built it. Now they have engineers and technicians who operate these systems in reality. Energy is the foundation of industrial power. The country producing steel, cement, aluminum, and chemicals more efficiently dominates those industries. Energy costs are huge components of heavy manufacturing. If China offsets significant portions through waste heat recovery, they've lowered global pricing. Western steel mills and chemical plants pay for all power used. Chinese facilities generate chunks internally from heat otherwise lost. That's thermodynamics. It's permanent. Cheaper steel means cheaper construction. Cheaper aluminum means cheaper vehicles. Cheaper chemicals means cheaper everything downstream. Productivity gains don't stay in power sectors. They cascade through entire industrial bases. CO2 as working fluid means you need a CO2 source. Industrial processes, steel, cement, chemicals, produce CO2 as byproduct. Instead of venting or spending money capturing it, you use it in supercritical power cycles. That turns liability into asset. Heavy industrial regions can generate clean power from their own emissions without external fuel. China faced pressure to reduce emissions. Supercritical CO2 doesn't eliminate industrial emissions, but eliminates burning additional fuel for power at those sites. That's significant decarbonization. Western countries offshored heavy industry, so steel mills and cement plants are in China, India, Southeast Asia. That's where waste heat exists. China will scale. The 30-megawatt Chaotan One plant proves the concept. The 169-megawatt test shows utility scale works. The next step is rollout across the industrial base. Hundreds of steel mills, dozens of cement producers, chemical complexes, refineries, smelters. Each is a waste heat recovery site. Equipment is modular, so installation timelines are short compared to traditional plants. Months instead of years. Power generated on-site feeds directly into facility grid connections. The economics are clear: free fuel, higher efficiency, smaller footprint, lower emissions. Every company installing one gains cost advantage over competitors who don't. That creates deployment races. China has industrial policy apparatus to accelerate it through efficiency mandates, incentives, supply chain coordination, and capital deployment. This isn't just about turbines. It's about who controls next-generation industrial infrastructure. Steam turbines powered Western dominance for over a century. GE, Siemens, Mitsubishi built empires on steam technology. But supercritical CO2 is different. Commercial expertise isn't in Schenectady or Munich. It's in Guizhou, Hebei, Beijing. China crossed from research to deployment first, gaining a decade-long head start in real-world experience. You can't catch up reading papers. You build plants, run them, break them, fix them, iterate. That takes years. Every year China operates these systems at scale, the experience gap widens. Western companies can license or build versions, but will catch up to opponents who've learned hard lessons and moved on. The West sees emerging technologies through disruption lens. Will this replace what we have? The market ready? What's the business model? Those slow things down. China asks, does it work? Can we build it? Then they build and improve while running. They don't wait for perfection. They ship the good enough version, learn from real-world operation, iterate in public. That's how they went from importing high-speed trains to exporting them in a decade. That's how they dominated solar panels. That's how they're doing supercritical CO2. The West invented the concept. China built the product. Once you're building at scale, you control the standard, supply chain, and expertise. The conversation shifts from, should we do this, to, how do we catch up? A much weaker position. December 20th, 2025. A turbine the size of a bedroom starts spinning in a Chinese steel mill. It doesn't burn fuel. It doesn't boil water. It captures heat thrown away and turns it into 30 megawatts of electricity. And 169 megawatts is already tested and waiting. Steam ruled for 140 years. That reign just ended. Subscribe and turn on notifications. The next story makes this one look small.